Let's take a look at a group of solutions that are called buffers or buffered solutions. Buffered solutions contain an acid and its conjugate base or a base and its conjugate acid. Now they have to be weak acids or weak bases. And what this does is it allows it to resist a change in pH when I add an acid or base to the solution. Okay. Their response to the addition of my protons or my hydroxide is based on Le Chatelier's principle. So let's say I have this buffered solution. And in this buffered solution, I added some weak acid and I added some amount of its conjugate base to the solution. Now I'm going to add some acid. Let's say I add HCl to it. I'm going to add some acidic proton. Well, that causes a stress. And in the stress, I increase my concentration of my proton or hydronium atom. So as a result, I have to shift to decrease the concentration. So I'm going to shift in the reverse direction. Because why? My reverse reaction will consume some of the added protons or hydronium ions. It will partially decrease the concentration of protons or hydronium ions. Likewise, if I add some hydroxide to my same buffered solution with my weak acid and its conjugate base, then what will happen is that the hydroxide will react with my hydronium ion to produce water. And so what this will do is it will stress my system by decreasing the concentration of my proton. So as a result, my buffer solution equilibrium will shift in the forward direction. And I'll shift in the forward direction to produce some of the hydronium ion and partially increase its concentration. Now, a buffered system cannot resist a pH change indefinitely. But what they can do is they can resist a pH change temporarily when a small amount of hydronium or hydroxide are added. They will resist the addition of the hydronium ion or proton until all of the conjugate base is consumed, in which case I'd force the equilibrium completely in a reverse direction. And after that point, then my pH will begin to drop. Likewise, it will resist the addition of hydroxide until all the weak acid has been ionized. And once that's done, then the pH will start to rise. Now, let's just look at the impact of having a buffered system. So let's say, for example, I have a 1 liter solution of pure water. So I have 1 liter of pure water, and I'm going to add 1 milliliter of 1 mole per liter HCl. Well, initially in my pure water, it has a pH of 7. But adding it to pure water is like diluting the acid. So as a result, I would change the concentration of the acid from 1 mole per liter to 0.001 moles per liter, which would cause its pH to become 3. And so the addition of this 1 milliliter to a liter of water causes pH to go from 7 to 3. What about in a buffered solution? Well, because it's a weak acid, we first have to do our ionization table and our ice chart and equilibrium expression. And what we find is that for acetic acid, if I had a buffered system of 0.1 moles of my acid and 0.1 moles of my conjugate base to initial, I would find that I have an initial pH of 4.74473. Now, yes, I have more sig figs than I should here, but I want us to be able to see the change. Now, if I add my 1 milliliter, I'm going to cause some moles of this to be converted into that as a stress. And then after the stress, I'll reestablish my equilibrium. And because we're assuming that all of this that was added is first pushed that way, what I get is I get a pH of 4.735. So if I was recording this at my correct sig figs, I wouldn't even notice or detect my change in pH. Whereas to pure water, it caused it to change by a value of 4. Now, to calculate buffered solutions pHs, or the amounts of my acid and conjugate base required, it can be difficult to do. However, we have what's called our Henderson-Hasselbalch equation. Now, we'll just go quickly through the derivation of the equation, but you just need to know the final equation itself. So let's say I have some weak acid, and it's going to ionize. I can write my equilibrium expression of it. I'm going to manipulate this expression to isolate for my concentration of my hydronium ion. I'm going to take the negative log of both sides. Then I'm going to apply some of my log rules to the right-hand side, distribute the negative on the right-hand side, and then now let's take this and we'll look at this. So, negative log of the concentration of H+, that's my pH. Negative log of my Ka, we call that our pKa. And then I can apply this. And so what we get is we get the pH of a buffered solution is equal to pKa plus the log of the concentration of the conjugate base divided by the concentration of the weak acid. Likewise, for a buffered system with bases, my pOH would be equal to my pKb plus the log of my conjugate acid divided by the concentration of my weak base. So how would this equation help us? Well, what if we were told the concentrations of our acid and our conjugate base, and we asked what would be the pH of the solution? Well, we know our concentration of our acid, we know the concentration of the conjugate base, and here I'm saying that the concentration of my fluoride is the same as the sodium fluoride because this is a soluble compound and it'll dissociate completely. I have my equation. I can look up my Ka value for hydrofluoric acid. So now when I substitute in my values, I get that I have a pH of 3.1299. So if we were to put this to correct sig figs, I would probably have given this with another one, and so this would be 3.13. Okay. How about if we're asked, what's the ratio of the concentration of my conjugate base to weak acid, so that I can have a pH at a specific amount? Well, I can write my ionization equation, just so I know. I can write down the rest of my givens. I know my pH, and I know my Ka, but I don't know the concentration of my two entities. My Henderson-Hasselbalch equation, substitute our values in. Okay. And then we follow the math through. So therefore, if my concentration of my conjugate base divided by my concentration of my weak acid is equal to 0.7, any combination of those concentrations will give me a pH of 3 for my solution.